Okay, so we got a couple really quick ones. With this one, a battery of EMF epsilon is connected to 3 resistors, a switch, and a capacitor as shown below. The resistor of resistor 1 is greater than that of resistor 2, which is greater than that of resistor 3. Which of the following correctly explains why resistor 1 has the most current than each of the other resistors, whether or not the switch is closed? So we don't care about what's going on with the switch, but we're just thinking, hey, why is I1 greater than I2 and I3? So the resistance won't really determine how much current we have. The current's more of a product of just the setup, the actual geometry of this circuit. So the resistance doesn't really matter. If it's going to go through that resistor, it's going to go through that resistor. When we're in parallel, then the current kind of has to make a choice. But in this case, we say, nah, it's not in parallel with anything. So let's see. It's located furthest away from the capacitor, which blocks current. That's just not true. I mean, eventually, yeah, it kind of like piles up, and then we won't be able to use that branch anymore. That branch will kind of be effectively shut off, but that doesn't affect the current in the meantime. Closest to the battery, not really. But yeah, this is the one that we want more. So the fact that it's the only resistor in series with the battery. So we know that we have this junction rule that says, hey, the current that's coming out of our battery, this current has to be constant everywhere. So in 2 and 3, our current is splitting. The current through the battery, which is also the current through the first resistor, has to equal the current of I2, I3, and then if there is any current going through C, or the capacitor. But yeah, so we know that, hey, this is in series with the battery, and this junction rule has to apply. The figure below shows a 10-volt battery connected in a circuit with 2 resistors, a parallel plate capacitor of capacitance C, and 3 ammeters. The circuit has been connected for a long time. Which of the following is correct about the voltage VC across the capacitor? Alright, so we've been connected for a long time. That's kind of our code word that this is fully charged up. So that's going to be at our maximum voltage. And if we think about what's happening here, this branch now is effectively closed off. Yes, we have this voltage across the capacitor, but it's not getting any more current. But if we think about this, is there any other paths that our current could take? Absolutely, our current could be going around like this. So if we look at our situation, we actually will have a voltage that is going to be less than 10 but greater than 0. And that just kind of is a product of our loop rule. So we could do our loop rule here if we wanted to and say, well, VC has to equal the voltage through the 100 ohm resistor. And we know that this 100 ohm resistor is going to be greater than 0 because there is current going through it, right? Because this is closed off, the current can still go somewhere, so it's still going to go somewhere. We can also do our loop rule. Yeah, we could do this loop rule. This one actually may be a little bit more telling. We have 10 volts minus the voltage through the 50 ohm resistor minus the voltage of the capacitor is equal to 0. That has to be 0 by the time we get back. So even though there's no current, it still has a potential difference. So we can say VC is equal to 10 minus a quantity. We don't even have to calculate it, but it's 10 minus something. So we know, hey, it's greater than 0, but less than 10 because of 10 minus. In the circuit represented below, the current in the 1 ohm resistor is 4 amps. What's the terminal voltage V of the battery? So in this case, we're seeing, okay, well, we have a current of 4 through here, which means if we use our Ohm's law, V equals I times R, the voltage in that resistor is going to be 4 times 1 is going to be 4 volts. So we also know, hey, if this is 4 volts, there's a because they're in parallel, this also has to be a voltage drop of 4 volts. By the time we get over here, we can use our loop rule and say, oh, okay, well, within this loop, we have to have a total of 0, or we just say, hey, they're in parallel, so they have to have the same voltage drop. If that is equal to 4, then we can find the current in that 2 ohm resistor. We can say V equals I times R. So we can say, hey, in this case, I is equal to 2 amps. So we have a current of 2 amps right there, current of 4 amps right here. And then what we can say is, well, we know the loop rule, we know the junction rule. We know that if we have 6 amps in this, we say, hey, well, this 4 and this 2 had to have branched off from 6 amps right there. We would have had to have 6 amps going into this junction because we have 6 amps coming out of it. So we can again say, okay, well, now we know the current through this one, that resistor right there. So we can say that V is equal to IR. So we can say, hey, our potential in that one is going to be 6 times 0.5. It's going to be 3 volts. So we have a 3 voltage drop through this resistor. And then we can say is, well, right here we have 4, we have 2. The current going into a junction has to equal the current going out of the junction. So we also have 6 amps coming out of the junction. We can use V equals I times R and say, okay, V right there is going to equal 6 times the resistance is 2 is going to equal 12 volts. So let's get rid of all this. And I'll just kind of write it in terms of voltage. So we got 12 volts right there, 4 volts right there, and then 3 volts. And now let's use our little loop rule. We can say, well, let's just choose any loop. There's a loop right there. I have plus the voltage from the battery minus 3 volts minus 4 volts minus 12 is equal to 0. So I can say voltage in the battery is equal to 12 plus 4 plus 3, so 12 plus 7 is going to be 19 volts, which is, there we go. Alright, so I just gave you a couple ones because my video was way too long.